So Laboratory 1 is split up into two basic components. The one part is an introduction orientation sort of to the course, while the other part is math stuff and other concepts. So that's the section we'll look at here. So first of all, just a quick periodic table summary. The periodic table represents the elements that we have in science. The periodic table has a couple things that are important to understand. First of all, the first letter is always capitalized. If it's a one letter, then it's just one capital letter. The second letter is always small. All right, so we have a chemical symbol. Each letter has an atomic number. Atomic number actually refers to the number of protons that are within that atom. We also have an atomic weight, which is the relative mass. It's actually an atomic mass unit. You can think of it as a magical unit or AMU. And those are important for figuring out molecular weights and things like that. So in terms of the periodic table, though, to be honest, there's not much more than maybe 20 chemicals that we have to worry about in physiology for the most part, because many of them are of somewhat minor consequence for the most part. So one of the questions that you'll see in the lab supplement ask you to make certain solutions and do a few other things. So the first question is, how would you make a 500 ml solution, right, that's 1 molar of glucose and also of sodium chloride? So think about that. Part of your prerequisites is chemistry. So, there's a few things that you probably, want to know. So first of all, what's a molar solution, right? So 1 molar means 1 mole of a substance per liter of solution, right? So how do you get to 1 mole? And so as an example, looking at glucose, right? What's 1 mole of glucose? Well, that's not that complicated, but let's do 1 mole of sodium chloride. So by definition, 1 mole is Avogadro's number, 6.02 times 10 to the 23rd particles. Also by definition, that 1 mole of substance equals its molecular weight. So let's go back to the periodic table, and we'll do sodium chloride because it's just a little easier to keep track of the numbers. So I look right here and I see sodium, right? Now remember, the chemical formula for sodium chloride is NaCl. So 1 Na, that's 22.99. We can round to 23, close enough for us. And then chloride, there's 1 chloride, and that's 35.5, good enough for us. So 23 and 35.5 is 58.5. So 1 mole of sodium chloride, 58.5, right, is what we will put into a liter of solution, and that will give us a 1 molar solution. If we have 500 mils, then how much do we put in? Well, if you have, just to kind of logically think about things first before looking at mathematically, if I have a liter of solution, that's 1,000 mils by definition, right? So 1,000 mLs is 1 liter, so 500 mLs is a half a liter. So if I put 58.5 in a 1 liter solution, right, in 1,000 mils, then I'll put half of that in 500 mils. So when we look at molarity, molarity is a way to look at the concentration. It's just one way to measure that. It typically has the units in moles per liter, all right, but it doesn't have to be. The darker containers, right, have a higher concentration, therefore a higher molarity as we move down from diluted on the left side to more concentrated on the right side. So molarity indicates the number of particles within a solution, and that becomes important physiologically for a number of different reasons. One of the big ones is in determining what's called osmolarity. Osmolarity determines where the movement of water goes, and so that becomes very important in terms of things. And we'll look at that in much more detail in lecture for the membrane dynamics section in the first lecture section. And we'll also see in the first lab for the second lab exam, lab 7-8 looks at molarity and osmolarity and diffusion and osmosis and things like that. So when we look at the molarity, we need to know what the molecular weight of each item is. We already did sodium chloride, and this one, probably could have put 35.5 here. So we saw that 23, right, for sodium, right? There was one of them. So it's 23. The molecular weight of chloride is 35.5. So we put it right here, though. And so we add them together, and the molecular weight of sodium chloride is 35.5 plus 23, which gives us 58.5 grams per mole, right? Sometimes we call those Daltons, but most of the time we just kind of go with the numbers and not worry about the units too much. Normally we care a lot about units in this class, but sometimes we're not going to worry about it. So for glucose, right, you have to know glucose has this very specific formula, C6H12O6. It's a carbohydrate. Carbohydrates generally have the formula CH2O when they're monosaccharides. That's the basic unit. So if we go back and look at the periodic table, so we have C, H, and O. So carbon, right, is 12 exactly. Right, we're not going to worry about that little 0.011. Hydrogen is 1 exactly, right, for our purposes. We're not going to worry about that 0079 after the decimal. And oxygen is 15.9999, which will round up to 16. So we know those molecular weights. You don't have to memorize them. If I wanted you to do that, I would give you a periodic table or tell you what those were, right? So here's the molecular weights for each one of those. Carbon is 12, hydrogen is 1, oxygen is 16. Since the chemical formula for glucose is C6H12O6, the number of carbons is 6, right? So we have 12 as the molecular weight times 6 of those carbons within glucose, and that gives me a total of 72. Hydrogen is 1. Remember from the periodic table, it's the upper left, right? There's 12 of them right here. So 1 times 12 is 12. And then oxygen has a molecular weight of 16. There's 6 of those. So 16 times 6 is 96. So if you add up 96 and 12 is 108. And 72 would be 110 plus 70, so 180. So the molecular weight of glucose is 180, which means 1 mole of glucose is 180 grams. 1 mole of sodium chloride is 58.5. Right? So as we said before, Avogadro's number tells us 6.02 times 10 to the 23rd particles. It's equal to its molecular weight as an atom, an ion, or a molecule. Now, when we want molarity, we're going to take the number of moles, right, per liter of solution. Okay? And normally you just do moles per liter. So how would you make a 500 ml of a 1 molar solution of glucose? You can solve this through a process called dimensional analysis. And basically, dimensional analysis is a technique where you cancel out different units and make sure that you have a ratio of 1. So we take what we know, and what we know is we want 1 mole in 1 liter, right, times 1 liter is 1,000 mLs. We know 180 grams is 1 mole, and we know we want 500 mLs. So if you look at this, the mole here and the mole there cancel out, the liter here and the liter there cancel out, the ml here and the ml there cancel out. What's left is the grams. And if you get 180 times 500 divided by 1,000, right, you end up with 90 grams. Again, you probably want to have a calculator and punch this through and practice it, but you just cancel it, and that's pretty simple. So, I think you probably should try to reason it out to make sure that your answers are reasonable. And it's a good check to see you didn't make a mistake. And that's true, all semester. So I'll give you an easy example. Let's say that you were looking at figuring out, we'll do this in the second lab, the average heart rate of the class. So if we looked at the average heart rate of the class and the lowest heart rate was 52 and the highest heart rate was 96, right? Where does the average have to be? Well, hopefully you all immediately thought in your head, oh, it has to be somewhere between 52 and 96. The average can't be 108 if every number is less than that, right? It can't be 42 if every number is higher than 52 or so. Estimate what you think the answer should be, and a good way to do that here is, okay, since 1 mole of glucose would be 180 grams, right, in 1,000 mLs, then if I had half of that, 500 mLs, then I only need to add half the 180 or 90 grams, right? So kind of see if you can figure it out the other way to see if your answer makes sense. For the sodium chloride, it's the exact same setup. It's everything that you need to do, except this time we use 58.4 grams, 58.5, depending on how you want to round. And we end up with half of 58, right, which is 29.2, or 29.25 if you use 59.5. So exact same calculation. So again, you can kind of figure it out the same way. Now, what happens if we want to know the molarity of a solution containing a half mole of NaCl that's in 2 liters of water, right? So again, there's a couple things we have to know. We have to know molarity is moles of solute, right, per liter of solution. So we set it up. So hold on. Oh, there it is. So we're just going to take the moles of solute and mathematically, right, divide both, actually multiply by both sides by liters of solution, right? So that would get rid of the liters of solution on the right side, and that would put the liter of solutions on the left side. So we'll get moles of solute equals molarity times liters of solution. Right? So we were given in our problem the molarity, 0.25 molar, right? So that's moles per liter, times 0.5 liters. We're given half a liter this time, not mLs, but liters. Right? So the liters cancel out. We get 0.25 times 5, which is 0.25 times 0.5, which is 0.125 moles. So that's a way to look at it. I think this problem's a good one to look at. What's the molarity of a solution containing 117 grams of NaCl in a final volume of 500 mLs? All right, so what are we giving? We're giving the 117 grams of sodium chloride, and we're giving a final volume of 500 mLs, or half a liter. Right? So first of all, you want to find how many moles are in 117 grams. I can do that in my head. I know that 1 mole is 58.5, and conveniently 117 grams is twice 58.5. All right, but mathematically, right, we should be able to do it. So we take 117 grams times 1 mole is 58.5 grams. All right, the grams of NaCl cancel out. I get 117 over 58.5, and that gives me 2 moles of NaCl. So I know I'm putting 2 moles in there. Now, we can also figure out, right, the molarity. Since My molarity is moles of solute per liter of solution. So in this case, I have 2 moles of NaCl. Remember, the 500 mLs is a half a liter, so 0.5 liters. So 2 over 0.5 is the molarity is 4. Okay, so the molarity is 4 if we put 117 grams of NaCl in 500 mLs. All right. So very similar problem with the NaCl and how it works. So you can go over these yourself, how it works. A 10% solution, you'll see similar questions in the first lab for those calculations you're supposed to do. So how do you make a 10% solution of glucose and sodium chloride? Well, what's interesting about percent solutions is they're really easy to make. One of the nice things about the metric system, one of the huge reasons why it really makes sense to use in a scientific standpoint, is 1 liter of water, right, by definition is 1 kilogram of water. Okay? Since 1 liter of water, right, is 1,000 mLs, right, and 1 kilogram is 1,000 grams, then 1 ml of water equals 1 gram. So that's really kind of a nice situation. So if I take 100 mLs of water, then I know I also have 100 grams. And if I do 100 grams, that makes my percent solution really easy to do. All right, because that's literally what percent means, is per 100. So if I want a 10% solution of anything, right, anything, then I just dissolve 10% of my total weight. So if my total weight starts at 100 grams, makes 10% really easy, I put 10 grams. So I put 10 grams of solute. That's something that will dissolve, right, in a solvent. So the solute plus the solvent gives me the solution. So that 10 grams of solute and 100 grams of solution would give me a 10% solution. So it doesn't matter whether it's sodium chloride. I'd have 10 grams of NaCl and 100 grams, and that would give me a 10% solution. I could have 10 grams of glucose and 100 grams. I could have 10 grams of Kool-Aid. It doesn't matter. As long as it dissolves, I can make a percent solution, right? So if I've got 100 grams, I should put 10 grams, whatever I'm trying to do in terms of that, right? Now, sometimes we use 100 grams for idea of using something called milligrams percent. You sometimes see that in some of the medical, not diagnoses, prescriptions and things like that, or some medical terms. Physiologically, you'll see milligrams percent sometimes. So, you know, we often, if we physiologically have fairly small concentrations of things, sometimes we go to milligrams or millimoles, or even micro or nano. As an example, some hormones are such low levels in the human body, we don't measure them in milligrams or even sometimes micrograms. Some of those things are measured in nanograms. And part of the reason is that medically we like to have whole numbers that aren't huge, right? So reporting something as 9.2, like would be like a protein, versus, you know, 190 for glucose, right? They're actually totally different units. Protein, as an example, is reported as grams per deciliter, while the glucose is measured as milligrams per deciliter. And so protein is significantly more concentrated in the blood than glucose. And so that's why we use these different values. So instead of saying for, you know, protein, 9,200 milligrams per deciliter, right? We just say 9 grams per deciliter. So we try to have these numbers that are, in the single digits, double digits, or triple digits, and adjust the values because of that. So something a little about values that you might see. So for percent solution, it's pretty easy to make. But how do those percent solutions compare? And without getting into too much detail, and this math right here in the middle, you won't understand probably at this point in time. But basically, since glucose has a molecular weight of 180 grams, and let's just round this up to make the math easy, sodium chloride has a molecular weight of 60 grams. Okay, since we made it 60, that tells us glucose is about 3 times heavier, right? Because remember, there's the same number of particles, right? Each one is 6.02 times 10 to the 23rd. In the case of glucose, right, we have the same amount of particles as we do in the case of sodium chloride. But glucose, because I have the same amount of particles, yet it weighs 3 times as much, then we have 3 times as many NaCl when we put in 10 grams, right? So 10 grams of glucose, right, is, also, let's do it this way, it's even easier probably. 180 grams of glucose is how many glucose molecules? Well, 1 mole, 6.02 times 10 to the 23rd. Well, if I want 180 grams of NaCl, right, and again, to make it easy, we'll say just round it to 60. Well, I need 3 moles, right? Because each mole is only 60 grams. So I need 3 moles to get to 180. So we already have over 3 times as many moles of sodium chloride in that 10% solution. In addition, the NaCl dissociates. It breaks up. So even though I put 1 particle of sodium chloride into a solution, it breaks up into an Na plus and a Cl minus. And in that case, right, I have 2 particles. And when I have 2 particles, that also adds to my osmolarity. And so basically, when you look at a 10% solution of glucose and a 10% solution of sodium chloride, the sodium chloride has 6 times more dissolved particles than glucose, which means it's 6 times more osmotically active, which would play a huge difference in terms of how they behave physiologically. So percent solutions are easy to make and they're easy to interpret in some cases, but then really difficult sometimes if you want to see what happens physiologically. So percent solutions we don't really use in physiology much. Getting back to this idea, okay, and talk about dissociation. Again, it's something you should have talked about in your chemistry class. So when we have particles that are held together by ionic bonds, ionic bonds tend to break apart, dissociate at when they come into water. So they're fairly weak, all right? And so what typical things are held together by ionic bonds? Well, there's 3 things physiologically we care about. Acids, bases, and salts are held together by ionic bonds. And basically then, when we put in an acid, a base, or a salt into water, that ionic bond is going to break apart and the molecules are going to dissociate, break into smaller sections. Okay? When we look at other molecules like glucose or a protein, they will dissolve in water, but they will not break apart. So every molecule of glucose I put into a solution stays a molecule of glucose. Every molecule of protein that I put into a solution, it stays a molecule of protein. All right, so it can get pretty complicated for a number of different instances, and so we're just going to stay with 5 different solutions in this class that we're always going to use for these types of problems, and we'll do them a couple times over the semester. So we saw previous slide that if we took sodium chloride, NaCl, which again, right, is held together by ionic bond. As a matter of fact, I think most of you would recognize this as salt, right? You put your salt in your French fries or whatever, right? That's NaCl. We stick it into water, it breaks up into Na plus and Cl minus. It dissociates. Okay. We also have a couple other solutions we're going to worry about. NaCl, right, is one of them. Okay. Another example would be CaCl2. That's another salt. It's called calcium chloride. When this breaks up, it breaks up into a molecule of calcium, a molecule of chloride, and another molecule of chloride. Remember the Cl2. Okay? So this has 3 dissociable particles. Right? Not on here, but I want you to take a second and consider KCl. KCl would be potassium chloride. All right, so how many dissociable particles is KCl? Give you a second. All right, hopefully you thought in your head, well, it's going to break up into K plus and Cl minus. And so therefore there's going to be 2 dissociable particles. All right. Now, one of the things we do in chemistry and physiology, we take some shortcuts. And for those of you that have a decent understanding of chemistry, you probably will not notice some of these shortcuts, or if you don't know much about chemistry, don't remember much, you probably won't at all even have an inkling of that we're cheating and taking shortcuts. Although if you're a very strong chemistry person, you may think, oh, well, that's weird. That doesn't really happen that way. And one of the points that I'm trying to make here is that we cheat on some of these numbers just to make our life easy. Right? So in this case, as an example, for sodium chloride, NaCl, we're going to assume that we have complete dissociation of all of our ionic compounds. Okay? So it says ionic compounds completely dissociate. That's a lie. They don't. Okay? As an example, sodium chloride has what they call a dissociation constant of 1.8. It means about 90% of the sodium chloride in a solution break apart, and about 10% stay together. And so you end up with what they call dissociation constant of 1.8. So it's easier just to assume that we have complete dissociation and not worry about dissociation constants. And it makes it close enough for some of the physiological things we'd worry about. So the 3 ionic compounds we're going to worry about, sodium chloride, calcium chloride, and then potassium chloride that I mentioned before. We're also going to worry about 2 other molecules, glucose, right, which has the chemical formula C6H12O6. What's interesting, about glucose, I think most of you recognize it's a sugar. You may know enough from other courses that you know it's a monosaccharide. It's a single sugar unit. You also may know enough from the course that any 6-carbon monosaccharide, right, like fructose as an example, would also have the same chemical formula, C6H12O6. So the monosaccharides that are 6 carbons are all going to have the exact same number of, the exact same formula, I guess is the same. So the number of carbons, hydrogens, and oxygens are going to be the same. Now, yeah, you can have 5-carbon sugars, which would be C5H10O5. Those would be the sugars that we see in, for instance, the nucleic acids like ribose or deoxyribose. But what happens with sugars, because they are held together by not ionic bonds, but by polar covalent bonds, which are much stronger than ionic bonds, they do not dissociate, they do not break up. Okay? Again, they dissolve in water, but they won't break up. And then the other molecule we're going to worry about is called urea. You're going to hate urea because it makes things more complicated. And urea is held together by covalent bonds as well, so it doesn't break up. So urea stays as 1 particle, as does glucose. So here's a nice table summarizing all of those things I just said. And one of the things that you'll look here in this second column, is the solubility in lipid. Is the molecule lipid soluble? Right. So a quick review of membrane solubility. Right. So a cell membrane is made of the lipid bilayer. Yeah, it's got other parts, but that's one of the major portions of it. And all of the ionic compounds, right, are going to not be soluble in lipid because you need two properties. You need to be small and nonpolar. Hey, you know what? You don't get a whole lot smaller than sodium, right? A single sodium ion is pretty small, okay? Chloride ion is pretty small as well. But the problem is you don't get much more polar than ion. So Na plus and Cl minus, while they're small enough to fit through the membrane, they're too polar. Same with potassium chloride, same with calciums and chlorides, so none of those can get through, right? In addition, glucose is polar, and it tends to be fairly large, relatively, speaking to sodium or chloride, right? So glucose doesn't go through the membrane directly appreciably either. It can get in through using proteins as transporters, but it can't get through directly. Now, urea is a little different. Urea sort of cheats a little bit. In the old days, when I was in school, we used to think urea was kind of special, and we used to say it was lipid soluble. And what happens is urea can cross the lipid bilayer and go from one side of the cell to the other. There's pretty good evidence now that it doesn't go directly through the membrane because it is a polar molecule, but it actually goes through channels. So basically protein holes in the membrane, specifically for urea, that allows it to go through. All right. So this explains the behavior of water that we talked about, and these are the number of sociable particles. If you don't understand how we get 2 for sodium chloride and 2 for potassium chloride and 3 for calcium chloride and 1 for glucose and 1 for urea, then you should just memorize this table. That's the easiest way to do it, and that's an important component of what we're looking at here. I will not ask you, for the most part, on an exam to do any other solution unless we used it as an example in lab, right? So as an example, in lab 2, we'll look at the behavior of HCl. All right, so HCl, I think you might recognize as hydrochloric acid. And earlier I said salts, acids, and bases are held together by ionic bonds. And when you put an acid, a base, or a salt into water, it breaks up. Again, we're going to assume complete dissociation. So just like the KCl here, right, we have HCl. So we're going to dissociate into an H plus and a Cl minus, right? So I would expect you to know that because we're going to do a whole lab on that. And the same thing with NaOH. Now, NaOH is similar to sodium chloride, right? So the OH is our hydroxide ion, right? And so NaOH, right, is a little bit different. It's going to break up into Na plus and then OH minus, okay? So it's going to break up into Na plus and OH minus. So it's still going to be 2, and that OH minus, because of the bond that holds the O and H together, is not going to dissociate, right? So you're only going to get 2 particles for that. So for exam purposes, we're really not going to have to worry about those too much. And these are the big 5 that you're going to have to worry about. And what it comes down to is this last column is very important with the dissociable particles. And because of that, let's go back here. We need the dissociable particles to figure out something called osmolarity. And osmolarity really refers to whether or not a solution will move across a membrane. And it's due to what's called osmotic pressure. And the osmotic pressure is due solely to the number of dissolved particles. Okay, so it doesn't matter whether it's a small or a big particle or charged or uncharged. It's just whether it's dissolved or not. So one sodium ion has the same, even though it's significantly smaller, One sodium ion has the same osmotic pressure as one dissolved glucose molecule. Okay, so we just have to know the number of sociable particles. And if we know the molarity and multiply it by the number of sociable particles, we can figure out the osmolarity. Okay. Now, again, this is another place where we cheat a little bit. And the reason why is, I don't want to go there yet. If you remember from chemistry, you probably also did, besides molarity, molality. And molality is similar to molarity, but instead of being the molarity moles per liter of solution, the osmolality, or in this case, the molality, is the number of moles per kilogram of solution. And so you have to add in the weight of what you're putting into that formula. And it becomes more different as you add more and more things into the solution, more and more solutes. So in dilute solutions, there's not a huge difference between osmolarity and osmolality. And since it's easier to do osmolarity, even though it really is osmolality we're concerned about, then we're not going to worry too much about the dilute solutions in the human body. So we're going to figure out osmolarity and just go with it. All right. And so if you didn't understand anything I said right there, don't worry about it. We're going to be in osmolarity. And if you did understand it, that's why we're in osmolarity, because it's close enough for our work here. So why does osmolarity matter? Well, osmolarity matters because it determines the osmotic pressure, which dictates how water moves. A number of years ago, the music station in Sacramento, when the Wii were popular, had a contest, and basically it was hold your Wii for Wii. And what they did is they had random people come in that wanted to try to win a Wii entertainment system. And what they did is they had them drink a half liter of water every half hour. And the last one to go pee was the one that won the Wii, right? So it was hold your Wii for a Wii. And there's a mom that drank about 7.5 liters of water. And what ended up, I'll just leave it on this one for now. And what ended up happening was, because the water was so dilute, it diluted the osmolarity of her blood. And as it diluted the osmolarity of her blood, that meant the osmotic pressure in her cells were greater, and her cells took up more of her water. We'll do an experiment in lab where we'll see that when we have a huge difference sometimes in the osmolarity, and we'll get your blood cells to literally blow up to lyse. It's called hemolysis. Well, there wasn't that big a change, but what happens is the cells of her nervous system, including her brain, got swollen and they didn't function, and she actually unfortunately passed away. So it can be very dangerous. And just to kind of look at it from a medical standpoint, right? Many of you probably understand, either by being in a hospital, working in a hospital, volunteering in a hospital, paying attention to medical shows and things like that, as an example, that one of the terms they use is like an isotonic solution for an IV. And isotonic means it has the same osmolarity as your blood. And you might as well learn it now. The osmolarity of human blood is pretty close to 280 what we call milliosmoles. Okay. And the reason why is it goes back to this idea that I talked about earlier. To figure out the osmolarity, it's molarity times the number of sociable particles. Okay. The problem is the molarity of most of the solutions we'll have is pretty small. It'd be like 0.28 as an example. And so we like to, again, deal with big numbers, so then we go to milliosmolarity. All right. The other number that we want to know sometimes is to look at what's called the equivalence. And the equivalence looks at the charges of the ions involved. And that relates to some degree about how well does something conduct electricity. So again, if we took sodium chloride and put it into water and it dissociated, notice we have a positive charge here and a negative charge here. And the easiest way to figure out the valence number that you'll use to calculate the equivalence is take the absolute value of the total number of charges. So Na plus would be plus 1. Cl minus, right, it's still 1, right? And the absolute value means ignore basically the negative sign. So that would be plus 1. So its valence would be 2. Potassium chloride would be plus 1, plus 1. That would be 2. Calcium chloride would be plus 2, because remember calcium has an ionic form, a plus 2, right? And then you have 2 Cl minuses, so there's a plus 1 absolute value. There's a plus 1 absolute value. 2 plus 1 equals 4. For glucose, remember it doesn't break up, it doesn't ionize, it's a neutral molecule, so it stays neutral. So it's got no charge, so its valence is 0, and urea is 0. So note that on the valence number, it's always going to be some sort of even number or 0 for our purposes in the class. Because again, these are the only 5 substances you're responsible for in most of the things we do in class, and especially on exams. Now, a couple other things about solutions. The solutions are sometimes expressed by the concentration of hydrogen ions. And the hydrogen ion we express in pH units. Okay? The formula for pH is the negative log of the concentration of hydrogen ion, or the log times 1 over the concentration of hydrogen ion. All right? So basically, it's the concentration. And as the concentration of hydrogen ion goes up, because it's 1 over that, it's inversely related, the pH, right, goes down. So here in the acidic area, right, we'll have a higher concentration of H+. So look at this little beaker here with a lot of H+, right? And the higher the concentration of H+, the lower the pH. Theoretically, the lowest level you'll have on a pH scale is 0. And in a pH of 0, it means literally every molecule in that solution is H+ with nothing else. Going the other way, right, is we're looking at the concentration of hydrogen ion. On the basic side, it's going down. And at a pH of 14, right, it tells us that there's no H+ in that solution, and literally every molecule is an OH-. Right? So what about a pH of 7? Well, pH of 7, right, I think most of you realize it's a neutral pH. And as a neutral pH, it tells me the number of H+, right, the concentration of hydrogen ion, is equal to the number of OH-, the concentration of hydroxide ion. Right? Human blood is right around 7.4. Okay, so it's a little more on the basic side, but it's pretty close to neutral. So one of the things to remember with the pH scale is when we look at the actual concentration, it's a logarithmic scale. Okay, so down here it says a log scale. So every jump on this is equal to a 10 times change in the actual pH units. So as an example, if you went from a pH of 7 to a pH of 5, what's the change in hydrogen ion concentration? All right, so it's a good question. So first of all, since the pH is going down, we went from 7 to 5, it tells us that the hydrogen ion is becoming more concentrated. Right? Does that make sense? So we know it's an increase in concentration. And since we went 2 units, right, so going from 7 to 6, it's a log scale, so that's 10 times. Going to 6 to 5, that's 10 times. So 10 times 10 is 100. So going from a pH of 7 to a pH of 5 gives me 100 times increase in the number of hydrogen ions, or the 100 times increase in the hydrogen ion concentration. All right, so that's pH. Uh, in terms of acids, right, they increase the hydrogen ion concentration, and bases decrease the hydrogen ion concentration, right? And then this is kind of setting us up for the lab. We'll also do in the first week of school typically is what a buffer is. And buffers help to maintain the hydrogen ion concentration. They help to resist changes in pH by preventing large fluctuations in the concentration of H plus or OH minus. The other thing that I kind of want you to get used to is dealing with conversions within the metric system and dealing with conversions between the metric system and our system. So I expect you to do that. And one of the things I want you to do is just sort of measure yourself, right? And I think most of you have an idea of what your height and weight are right now. It doesn't matter how close you are, really. So let's say someone is 6 feet 2 inches tall. Okay, so if they're 6 feet 2 inches tall, the 6 feet gives them 72 inches, and the extra 2 inches is 74. So how many centimeters are they if they're 74 inches? And so you should be able to convert 74 centimeters, right, into, sorry, 74 centimeters, 74 inches into how many centimeters, okay? So you should be able to do that math, and there's examples there. And the same with weight, pounds and kilograms. So someone who's 74 inches, you would multiply by 2.54 centimeters per inch. The inches would cancel out, and you'd end up with about, 188 centimeters. Going the other way, right? What happens if someone's 150 pounds? Okay, someone's 150 pounds, right? You do 1 pound times 0.454, right? Kilograms per pound. So this time we're going to have the pounds cancel out, and instead of multiplying by a big number, we're actually multiplying by a smaller number. And so in this case, we'll end up with about 70 kilograms as 150 pounds. So one of the things that you can kind of do, and it kind of gets back to that idea of estimating, is you can estimate what those numbers should be. And it's stupid, and I know it's not really true, but many people wouldn't mind being a little taller, and many people wouldn't mind weighing a little less, right? So one of the things you can think about is you look better in the metric system. It's kind of a good check, which means that going from inches to centimeters, centimeters should be bigger than inches. But going from pounds to kilograms, kilograms should be smaller than inches. Sorry, smaller than pounds. So, the biggest mistake I see in these type of conversions are students that multiply when they should be dividing, or vice versa. And so they say, oh, a 150-pound person, right, weighs 332 kilograms, right? Oh, wait a minute. Kilograms is supposed to be less than pounds. I'm supposed to divide, not multiply. And it's kind of a good little check to make sure you're correct on those for that. So there's what I just said in terms of looking, better in the metric system. So you can read that. So here's a way to convert units. If we had somebody who was 66 inches and 120 pounds, you have 120 pounds times 1 kilogram over 2.204 pounds. So those cancel out. And that gives me 54.5 kilograms. Or you go 120 pounds times 0.54 kilograms per pound. Gives me the same answer. For 66, you multiply by 2.54. Or you divide by 0.394. It doesn't matter which one you do, as long as you do that dimensional analysis and make sure you're canceling the inches and being left with your centimeter units. All right, so there are some other things I want you to try in the lab book, and it'll show you how to do some of that and a few other things if you want. I'm not going to do these because they're part of your homework, and you come back and look at those when you need to later. So that's kind of a nice review of what we're doing for Lab 1 with the conversions and the measurements and things like that. So that's the one part of it with the calculations.